Hello. In this tutorial, which is the second tutorial in the series on Python, within the series on tutorials introducing the software typically found in robotics, we are going to look into some common Python packages, specifically those for mathematics and visualization of that same mathematics. Like I mentioned in the previous video, the default lists in Python are dynamically linked lists, and you don't want to do math with this on this. This is going to be super. It's going to take forever. You want a real proper array, so that everything is contiguous in memory. I also mentioned that Python is written in C, and that you can define functions in C and then use them in Python basically, but they're executed at C speed. And the arrays are basically imported, are defined in the package called NumPy, and it has a bonus for a bunch of different math essentially. One additional point of information if you want to harness this speed as much as possible is to have all of your variables defined as these arrays. And when you do this it's called vectorization. You have vectorized code. And that way you harness. You can write something that relies only on the NumPy in Python so that it's nearly as fast as C. If you pre-allocate all of the arrays, you don't, copy construct this and that. Anyway, point is, once you use NumPy, you want to use as much of it as often as possible, and it really has like a crazy amount of predefined functions that you use. So very good package, very good for math. Use it as much as possible for doing math. The way you would define some sort of a vector or a matrix is, you would put in some sort of floats. Why can't I type to save my life here? Like this. Now that would be a NumPy array. In fact, you can even set the specific float size that you want by doing a d type over here. D type is NumPy dot like float 32. I think in Python everything by default is double. But yes. And now with this you can do things like addition. If they're the same size, it's going to work. If you have a different style array, I should have mentioned you can't append on this because it's an array. It's fixed size, right? So these are not your Python lists anymore. You can do things like powers on them. This bunch of them by default are element wise, so keep this in mind. This is what I wanted to show here. And if you want to define a matrix, then you would go in the, I don't really need this. You can just do a double list basically. Let's just copy this real quick. Like that. This is a feature of my terminal. I just don't want to type, though. I could have typed out by now. Okay, now you have a matrix. If you go for shape, it will give you the shape. So it's 2 rows, 4 columns here. I think if you square it, it will again be element wise, and nothing is stopping you from turning this into a tensor, and you can still do your operations like this. Now the way you would multiply a matrix is with this @ symbol, and thankfully you get errors that are relatively descriptive, like, oh, I can't do this because the sizes don't match, but if I do a transpose, then they will be fine. this operator is an overload of something else, and basically, yeah, it's like matrix multiplication. But if you would to go for Matmul, that would be the same thing. So this is like just a like slightly nicer way to write it down. Of course, normally all of the functions are defined, yeah, as other Python functions basically. Let's see what concatenate does. Okay, not what I wanted immediately. I'll go how you can find out more relatively quickly. I also just want to say that it has a bunch of ways to predefine an array. So if you do I, that would be an identity matrix. And there's a bunch of them like this. Very, very often when I'm trying to test something out to see if I have my math on paper and I'm not exactly sure how to do it in NumPy, I would allocate like a random matrix, and then you can give it the shape. If you're giving it the shape, you need to pass a tuple, something like this. And now I have a big array of numbers, and I play around with the numbers to see what's going on. Now let's try to do the most classic possible operation, which is the matrix inverse, and there you go. We have a matrix inverse now. That's about it that I want to show you right now. Let me just remove my face. What I want to advertise as much as possible is to use the documentation that's already available. So now I just show you that it's not scary and like told you, the few facts about it. But if you really wanna know a bit more, oh, that's the ugly one. Then you would type in the documentation. Again, if you're looking for something specific, just type in how do I do a matrix inverse, how to do a matrix inverse in NumPy. Go to Stack Overflow. Oh, I can't do it, blah blah. Do this, as easy as that. So if you have a specific question, just put it in. Use ChatGPT, it certainly knows it, whatever. But it is very important for you to know what things even exist so that you can, ask the right questions. And for this, I really recommend going over the beginner's guide. So essentially kind of what I did, but it much more words with a bit more examples. So NP arrange, which gives you a sequence, a length space, where you do basically equally distant numbers from one another. So that would be very useful if you just want to define, like, you have some time that you follow for 2000 seconds, let's say, and you want the fidelity of very small fidelity. What is this? The number of steps. That would be the length divided by the dt, let's say 0.01. And I need to cast it as an integer in this case. Okay, but now you have like a very, very, very big range of time. And then, you do a sinus of this time, and it just works. You see, it was really fast, but if we look at the number of points that was here, was what, 200,000 points, so this is very, very powerful stuff, and it's very good to like I said, use as much of it as possible. So here we go over some concatenations and so on, whatever it is. One particular thing that I would absolutely recommend, I think it's would be the indexing. The indexing is crazy in NumPy, and it's crazy effective as well. So you have the basic stuff like how do I index an element of a matrix and so on, but there's this concept of slicing, where you can go through some smaller part of your array in this way, and you can slice that through matrices. So you can select a sub matrix basically, and this is something that you relatively often want to do, and this guide tells you a bunch of gives you a bunch of examples on it. And also what's very, very nice is that if you do this particular weird kind of syntax for example, you have your array X, you want to select only the numbers that are smaller than, you want to add, let's say 20 to everything that's smaller than it. You can do it in this one single line. You know, you here select everything that's smaller than 0. So that would be these two things, and then you would add 20 only to that part. Okay, so play around with this. Yeah, the syntax might be a bit weird, but this is I highly recommend doing this. Maybe one thing to mention is a piece of syntactic sugar called list comprehensions, which is this is like how you would use it like 90% of the cases. I'm missing the I here for wrong spot. There we go. So in this way, basically you do a for loop where you use the index or something else. Doesn't have to be that. I could just say, you know, give me a string. But this is like a combination of creating a list and a for loop, which, you know, instead of like 5 lines, you have this single line. You can do this with dictionaries as well. Let's say yeah. So this is in conjunction with this you know, a bit of like crazier syntax. You don't really have to know this, but I highly recommend getting into it. It will make your life much easier once you get over the hump. Okay. That's about it that I want to say about NumPy. We'll a bit later go into Matplotlib, which is how you can plot NumPy arrays very quickly. I want to put my face back on. Not really. The second, no, I do. Sorry. There we go. Now I want to talk a bit about SciPy. So let's import SciPy. SciPy is a collection of mathematics that is built upon the NumPy arrays. So like I said, I mean, you know, you can do a matrix inverse in NumPy, but if you do want to do a bit more, something a bit crazier, let's say a matrix logarithm, you would use SciPy most likely. Again, if I hit it with a question mark, I get some immediate documentation in IPython. I forgot to show that to you last time, but yeah, this is, you know, very quick way to see, you know, if you get an error because the program was expecting something else. If you hit it with a question mark, this is like the way to see what this particular function wanted. And again, you play around with it until you get a correct result. Essentially, that's. These things go very often. Okay, so we now computed a matrix logarithm. There's, you know, stuff like within the linear algebra. Okay, I said math. I'm showing you linear algebra. We're going to get to other things as well. Okay, give me a square matrix and a fractional power. A and I don't know. Let's say minus 0.555, and now I can get this as well. So, you know, very powerful stuff. If you want, of course, this is much easier written down to see what this is written down on paper. I would recommend that you first, you know, if you're doing something crazy with a bunch of steps, some wild mathematics, that you have to go step by step, that you verify everything. And that you try to document your code a bit. And of course, you have everything pre-written on paper. You know, sometimes you want to, well, I mean, I fall into this trap relatively often, where you want to write something down very, you know, as quick as possible, but you're not 100% sure how it looks, and you just start coding right away. It's very easy to get lost in the sauce, you know, because this would be A, and then in the superscript you would put the, you know, the power. That would be it, and it looks like a whole line there. So while it's super easy to use, if you're doing, you know, something serious mathematically, have things written on paper and then just transcribe them into code. I think that's the easiest way to go about this. Okay, SciPy docs again. they're quite good. Well, a bunch of these like popular things in Python are very well. They're very good. We have the user guide, which there's a bit when you go a bit more tutorial type things. If you go to the API, then you'll see just the more brief way the different functions that exist. Sometimes you want one thing, sometimes you want the other. In the beginning, you certainly want these more tutorial type things. Let's just go over one particular example to see roughly, just so that you have someone tell you, hey, this is how things should look before you dive head in. Now, I don't know if you'll use optimization for anything, but I just want to show it around a bit so that you have a feeling for what's out there. No, I didn't want this example. I think I pre-selected something else. It looked a bit nice, a bit more nice. No, this is fine. Okay, so let's say you have a multivariate function that you want to. Did I remove my face? No, I didn't. Maybe we can just. Okay, let's do it like this. This is still visible. So yes, you want to use you have your multivariate function that you want to minimize, and you want to use the Newton conjugate gradient method. I mean, there's other ones. The other ones you would go over here to optimize. See what's there basically out of these minimization algorithms. And if you aren't familiar with one of them, you can find its Wikipedia page if this isn't enough information for you. But anyway, you have this algorithm. So very typically in SciPy, you want to have your functions defined. So you could numerically calculate a Hessian, for example, with finite difference methods, but typically things work much better if you have it defined analytically. There is a symbolic math package, but that's for the next video. That's not as often used. So anyway, here you would define your Hessian analytically. You've written it down on paper. This is like what I like about this documentation. It gives you very nice mathematical representation, and only then do you go into the code. So Rosen function is, I'm assuming, defined somewhere upstairs. Yeah, okay, that's the function. So it's just you do some math. Again, these x's or whatever they are NumPy arrays. Let's go back to where we were. Wasn't even this example, but I mean they all sort of look kind of the same in the code. You define your derivative, and then you call for the minimize function. You give it your objective function. You give it an initial point. You tell it which method to use. You provide your function for calculating the Jacobian or a Hessian, like that full Hessian example, wherever it is now. Wanted, and then you do some different options. You tell it to to run with this minimize. It spits out some information. You get your results. You're good to go further. And this as well has it's a wrapper around some ancient Fortran code or whatever. Okay, there are a bunch of things in SciPy that are very interesting. Integration is very interesting. If you're doing signal processing, you have a bunch of things. There, linear algebra, like we mentioned already. Interpolation, a bunch of like the things that you sort of want to exist so that you don't have to, start from scratch. They're here already, which is very nice. Okay. What's next for us here? Matplotlib. Okay, for this, I actually do want to, okay, it looks fine. Go back here. So Matplotlib is in 99% of your, basic cases. It's of course built on NumPy. very Matplot. There we go. When you do an as something, it's just this, but in less letters. Yeah, anyway, the Matplotlib, very intuitive functions. You could just, play around with the shell to discover like half of them. There's a gallery that I'll show quickly, but anyway, the way this would work would be, I have my, okay, maybe I don't want as many points for this. For the plot, I think 200 points for any plot is pretty much enough. We have 2000 here. And let's say, my function of time is the sinus. And now I want to plot this sinus. So plt.plot, this would be a line plot. Y, and then I hit it with a plt.show. And I get my, okay, maybe shouldn't have chosen such a long time step, so this looks like, fairly ugly. Let's recalculate everything. If I go this sort of functions like a bit of like the command line interface, so I can go up and down, find my things. Anyway, where was my plot? And then again the show. And okay, now it's a part of the sine function. How the hell did I get it there? There we go. All right, so there's scatter plots and so on. Anyway, the absolutely best by far. Where was my? Oh, I'll just open it up again. The best way to find what Matplotlib has to offer by far is the examples. Very nice set of examples, and they offer you the code for this as well. So I don't know, let's say you want scatter plot with histograms on the side. There's your code right here. You can very easily copy it. You put it to a script, you change it to what you want, and you're good to go. So just scroll through the gallery, find what you want. It's pretty amazing what you can find here. Very advanced things. In fact, like I don't even know what this is, but it looks cool. Okay, then finally I want to show you a bit about how I used Matplotlib personally. Let me see, where did I have all this? Okay. So a bit of this code is developed during my my master's, but like now during my PhD, I would say that they're fairly involved examples. Some of them include animations as well. What do I want to run here? Main for question 1. Sounds like a good thing to show. Maybe not. Let's see. Okay, so the way I developed this particular plot, this is like the blue are SIA model of infections. So suscepted, infected, and recovered, or SIR, I guess then. Anyway, this is just a scatter plot. There's some like logic for how these things interact, and there's the simplest possible way if you want an animation would be to use a program called Celluloid, which is very inefficient. It plots every single time step one by one and then just chains them together. But there's no easier way to use it. You give it the figure. I'm assuming, yeah, okay, anyway, it exists. You can find the docs for it. There's a very similar thing going on in the other thing here. There's a video. So this is simulating like some simplified model of forest fires where basically if the trees are connected or whatever, then a lightning strikes, and then the amount, everything that's connected burns down. It just like looks kind of cool. There's nothing really special going on in this. It's again like scatter plots basically with 2 different colors, and that's it. Okay. Now to get something like a bit more involved, now this one I know that it's a video because it's sort of, it's reading something from the network, then plotting that. It's sort of visualization for a car. We have the, yeah, okay, I did write the whole path down. Yeah. So this would be a car navigating around a some sort of a maze. Then it finds all the points where it wants to go, and it's sort of, yeah, it's just trying to get to this top point. And this I think this was a scatter plot as well. And then you have just a line going between 2 points, and this is a patch called a rectangle. And this animation was done in a bit with blitting. So everything that's you basically only change what's been updated in the plot. It's just gonna do some reparking here. Okay. And then finally, I mean, you can embed your plotting within a graphical user interface so that you can click on things and then interact with it. There's actually something that I did relatively recently. I wouldn't really, I'm having a hard time recommending whether you should do this or not. For some cases, it's absolutely the best. For others, there's probably other software that's a bit better. Now, I've just gotten used to this NumPy Matplotlib stack to the point where, yeah, I know how to use it for a bunch of these different things. Anyway, so this was a combination with TK-inter. And here you have some two different inverse kinematics algorithms that are going to the same point, and the idea is to sort of analyze how they perform a bit differently. This ellipsoid here is what's called a manipulability ellipsoid. It tells how easy it is for the robot to move different points. You know, now I hit on a neuron, I get something else. Can turn these ellipses off, so it's maybe a bit easier to see. It's a bit janky because of some of the things I did. It like leaves the previous, so sometimes you need to update it a bit manually, you know, to delete the previous thing that was there. And yeah, you can have, you know, tabs, and as time goes along, you know, it's all kind of connected a bit. Yeah, so you can do kind of fun things with this. I think the solving, well, I mean, the mathematics for this is like a bit more involved, but yeah, you can select a different algorithm if you want. Let's do something like this. Generate a neuron. It's not pretty, there, can't do a QP, it's gonna complain. I know I don't have a particular thing installed, you know, and then if I hit on play, going to run and see one of them is near a singularity, so it's shaking around, while the other one is pretty tame in this case. Okay, so you can do fun things with Matplotlib and Python if you know put it in a GUI as well. With not too much work, but you know it really depends whether you want to go all the way with this or not. Certainly for, you know, 200 lines of code to optimize something and plot it, as you saw, I mean, it's fairly simple. And as you will see in the documentation, you know, there's a bunch of examples. You download the example, change a thing or two, and you're good to go. But I just wanted to show it to you. If you want, can go a bit further with that as well. All right, I hope you learned something with this. There will be another video which just quickly mentions different packages that are quite neat. And with this, happy solving of math and coding up of the math.